Hi guys, welcome back. We will continue our discussion on transformers. Like we have discussed about basic principles of an transformer and how it works and how the construction of an transformer have taken place. Now we will discuss about transformation ratio. We have two types of transformation ratio. One is voltage transformation ratio, and that is current transformation ratio. We use transformer for basically for two major purposes. One is for voltage step up or step down, voltage up voltage up or voltage down. For another purpose is current up or current down. That means I'm not saying current up and the current down in the sense my intention is not that uh, to make the current flow upwards or to make the current flow downwards. My intention is that uh, magnifying the magnitude of current or demagnifying the magnitude of current. These are the two major purposes for which we use transformers. First, we will discuss about voltage transformation ratio. Voltage transformation ratio can also be defined as the ratio of secondary voltage to the primary voltage, denoted by K. That in the sense, V2 by V1. This is the voltage transformation ratio, K1, K, we will. And K is equal to this. K is equal to V2 by V1, E2 by E1, N2 by N1. Where V is the voltage in the winding, voltage of, I mean, primary voltage. V1 equal to E1, but E2 will never equal to the V2 because there are some other things in it. Like I will discuss it later. Okay. K can be represented as V2 by V1, that equal to E2 by E1, that equal to N2 by N. Just remember this. And current transformation ratio. Consider an ideal transformer where we have input volt ampere is equal to the output volt ampere. Mathematically, input volt ampere is equal to output volt ampere. That in the sense V1 I1 equal to V2 I2. That in the sense we don't have any losses in the transformer. Whatever the energy supplied is going out from the transformer. Just think of this situation. Then V2 by V1 can be written as I1 by I2, right? But we know V2 by V1 as K. Now we can write K is equal to I1 by I2, V2 by V1, that is equal to E2 by E1, that is equal to N2 by N. Ah. Now I will discuss about what is meant by step-up transformer and step-down transformer. If a transformer step ups the incoming voltage, then it is known as step-up transformer. In the sense, if you are getting some amount of voltage, in the sense we are getting 11 kilovolts voltage to the transformer, but we need somewhere around 25 kilowatts of voltage. Now we will use step up transformer in that scenario to step up the voltage to meet our requirements. In some of the scenarios where we might have got 11 kilowatts line and we have step down it to 220 watts and 250 watts. There we are going to use step down transformer, which is going to step down the voltage of incoming energy, and it will send it to the whole circuit. That is the difference between step up and step down transformer. Now we will discuss about losses in the transformer. Yeah, in transformer we have two types of losses. First is iron loss, second is copper loss. Copper loss, as we discussed, right, in this windings are made up of copper wires. So this copper loss will occur in windings. This iron loss will occur in the remaining all parts of transformer. Now, in iron losses, we will discuss about first iron losses. The iron losses. This is the power loss that occurred in the iron part. This losses is due to alternating frequency of EMF. The iron losses is further classified into two losses. One is eddy current loss, and another one is hysteresis loss. Like wherever the power is lost due to iron parts, that type of losses are known as iron losses. In even in iron losses, we have two types of losses. One is eddy current loss, another one is hysteresis loss. Eddy current loss. The power loss is due to alternating flux linking the cores, which will induce an EMF in the core called eddy EMF, due to which current called eddy current is being circulated in the core. As there is some resistance in the core, with this eddy current circulation convert into heat called the eddy current power loss. Eddy current loss is proportional to the square of the supply frequency. This is according to our discussion. This is the core, right? And primary limb and secondary limb. We are going to get some flux induced over here. And this flux is going to pass through our secondary limb. After passing through this secondary limb, this will continue its direction, right? Due to then it has to pass on through this again through this what we call primary limb, where we are applying some voltage and we are getting some flux, and this flux is opposing that flux, opposing the flux induced due to applied voltage. So we are generating some what we call opposition to the generation of flux, which will induces heat in it, heat in this limb, which are which has to be dissipated from this limb. These are eddy current losses. Okay, I hope you guys got an idea. Now, hysteresis loss. This is the loss in the iron core due to the magnetic reverse in the flux core, which results in the form of heat in the core. This loss is directly proportional to the supply frequency. Eddy current losses are proportional to the square of frequency. ED losses are directly proportional to square of frequency. Hysteresis losses are proportional to frequency. Just keep these things in mind. Uh, we will move on to copper losses now. Copper losses. This is a power loss that occurred in primary and second coil that when the transformer is on load. This power is wasted in the form of heat due to resistance of the coil. This loss is proportional to the sequence of the load sequence of the load. Hence, it is called variable loss, whereas the iron loss is proportional to the constant loss. And as the supplied voltage frequencies are constant, like here we don't know whatever the load that we are going to apply. So we cannot judge the amplitude or magnitude of this copper losses. But whereas iron losses are considered, it is proportional to the frequency or square of frequency of the incoming input voltage or input frequency. This is a brief note about losses in transformers. Now we will discuss about efficiency of a transformer. Whenever we will discuss about efficiency, we will came to we will discuss about this formula like output by input. Input can be written as input is equal to output plus losses. That's it, right? That's what here written over here. Efficiency is equal to output by output plus iron losses plus copper losses. Iron losses plus copper losses is the total loss. Now we are going to substitute uh, its respective values. Output power can be represented as VE2 I2 cos phi. Why we are taking cos pi over here? We discussed right in the first class of that alternating current. We are going to take imaginary real part plus imaginary part. How a complex number can be represented in cos and sine functions. Cos pi plus I sin pi, right? Where cos pi is an real part, I sin pi is an imaginary part. So we are going to consider only real part, which is what we call cos for the real world scenarios. So we are considering only the real part. V2 I2 cos pi by V2 I2 cos pi plus losses. That is the formula. The transformers are normally specified with their ratings as kVA. Therefore, efficiency can be written as kVA into 10 cube, means I'm converting this V2 I2 into kVA, that's it, into cos pi, and same kVA into 10 cube into cos pi. These iron losses will be will be given in VA, I mean volt amperes itself. You are going to directly add it to this thing and you are going to find efficiency. Don't worry. Yeah, that's it. Condition for maximum efficiency. In a general, for efficiency to be maximum for any device, the losses must be minimum. Between the iron and copper losses, iron losses are fixed losses and copper losses is a variable loss. When these two losses are equal, also minimum, the efficiency will be maximum. Right? That is the point. When a efficiency equal to output by output plus losses. If this losses is going to decrease, then this whole denominator will decrease, right? If denominator decrease, the whole fraction will increase. So whenever we are going to get least losses, then the efficiency will be maximum. In this case, if copper losses equal to iron losses, then we are going to have least losses. So condition for max efficiency equal to iron losses equal to copper losses. That's it. Now we have another one small topic called as voltage regulation. The voltage regulation of a transformer is defined as a change in secondary terminal voltage between no load and full load at a specific power factor expressed as a percentage of full load terminal voltage. In a sense, voltage regulation in the sense, uh, change in voltage between the terminals when there is, if no load is applied, we are going to have some potential difference between the terminals. When we applied some voltage, I mean some load to this transformer output, and we are going to what we call measure this voltage across these terminals. The difference between uh, voltage when there is no load and when there is full load, that difference is known as voltage regulation. And I'm expressing voltage regulation in percentage. No load secondary voltage minus full load secondary voltage divided by full load secondary voltage into 100. This is the voltage regulation formula. Just go through it. That's it. I think we discussed a lot about these transformers, guys. Single phase transformers. I'm just keeping full stop for this topic here in this video itself. So from next video onwards, we will discuss about DC motors and DC machines. That's it, guys. Meet you in the next video. Bye.